All right, the last short answer paragraph from Unit 1 is a dart launched at an angle. A launcher is used to launch a dart with an initial speed of v from a table at an angle as shown in the figure. The dart exits the end of the chamber at a height h above the floor and lands a horizontal distance d from the end of the launcher. A close-up view is included that shows the dart in the launcher immediately before being launched. Inside the launcher, the dart rests on a platform with negligible friction, and a compressed spring is released to push the dart out of the launcher. Assume air resistance is negligible. And then up there you've got your y and x axes. X is out to the right and y is straight up. Then they show us here, for part A, a free body diagram of the forces exerted on the dart while it's being launched, as is shown there. So we're going to describe what changes would need to be made to the diagram to make it a correct diagram for the dart when it's in the air. Now, this is what I'm talking about. Like, we're going to practice free body diagrams because they're going to ask stuff like this. You can't make one, but you can certainly tell how it needs to be amended. So, part A, once the dart is launched, it's in, yeah, you're right, free fall. So the free body diagram would just look like this. Now, they don't ask you to do it. We ask how to change things. So we get 1 point for saying removing the normal and spring force. Or you could say the only force acting is gravity because you don't even have to say because it's in free fall, but that's why. So you get a point for realizing that the object is in free fall. So good start already. Part B gives us 3 graphs, the horizontal versus time graph, horizontal velocity, the vertical velocity versus time graph, and the acceleration versus time graph for the motion of the dart from the instant it's launched until right before it hits the floor at time t sub f. B asks us which of the graphs could lead to a determination of the distance d and how could you do it? Well, the area under a velocity versus time graph is a displacement, so that's a possibility. The area of the acceleration versus time graph could give you, I suppose, the average velocity, but we want displacement, so we're looking at the velocity graph. So then you have to ask yourself, well, which one do I use? Hopefully it makes sense that to find the horizontal distance, we use the horizontal velocity versus time graph. So you get 1 point for realizing that we want to use the horizontal graph, and then you get a point for saying that you need the area under the curve, and I would say again between 0 and TF, although they kind of have it marked there. So 1 point for realizing which graph to use and another point for how to use it. Now we're on to the paragraph. And the paragraph says, after the dart passes the highest point of its trajectory, the angle between the velocity vector of the dart and the horizontal, or the x-axis, continues to increase until the dart strikes the ground. In a clear, coherent paragraph, explain the following. Why is the angle of the dart's velocity in the horizontal continue to increase? And why, no matter how large that height is, why is the angle never 0? And so in effect, why can a projectile that's launched at an angle never nosedive? Okay, why is it always going to land at an angle? So what I wrote is, as the dart leaves its highest point, right, at the highest point, the x velocity is what it is, and the y velocity is 0. And so our angle there is 0. But after it leaves its highest point, the value of the value of the vertical velocity increases because gravity is accelerating it. The horizontal velocity remains constant because we're neglecting air resistance. So since the vertical component of velocity continues to grow and the horizontal component stays the same, and since the angle of velocity is the combination of Vx and Vy, right? As Vy gets larger, this angle gets bigger, okay? Now, that's why until it hits the ground. Now, why can this angle never actually be 90 degrees? Well, in order for that to happen, our Vx would have to be 0, and that's never going to happen. So that's the gist of the argument there. Here's how the rubric breaks down. You get a point for saying that the x component remains constant. You get a point for saying that the y component increases in magnitude, right? You get a point for indicating that the resultant vector velocity is equal to the vector sum, oopsie, Vx, I guess it's squared, plus Vy squared, right? Or I guess it's equal to the sum of Vx plus Vy, however you say that. I wrote the resultant vector is the sum of its components, or you could maybe say the angle is formed by the components or something like that. You get a point for saying there will always be an x component. All right, so theta will never be 90 degrees. And then you get a point for the clear, coherent paragraph that addresses the question. And then they throw this bizarro part D on here, which I don't know. I don't like it. It says the dart is now launched so that it collides and sticks to a wheel. At the instant, its velocity is completely horizontal, as shown above. The wheel is free to rotate about a pivot at its center that has negligible friction. Indicate whether the linear momentum of the dart wheel system will be constant during that collision and justify their answer. Now, as much as I don't love this question, I'm afraid you're going to get a question sort of like it because you only get 2 FRQs this year. So they have to assess 7 units of content with only 2 FRQs. So you can bet the farm that they're going to combine them somehow. This just seems like an oddly very weird way to combine them. The answer is that no, the linear momentum is not constant because there's an external force on the wheel, okay? The external force on the wheel. And gravity is also pulling the dart wheel system. So if this were on a horizontal, table and the dart was coming at it from the side, it would be a different story here. But you get 1 point for saying that it's not constant if you attempt an explanation. The reason it's not constant is because there's an external force on the wheel. So whenever you get a question that says, is this constant, is that constant, and they ask you why, remember the parameters for momentum to be conserved. For example, there can't be any external forces. For energy to be conserved, there can't be any external work done on the system. So don't let that why question make you like Bambi in headlights, right? There's probably a reason you answered no, and it's probably something like, oh, there's an external torque, so angular momentum's not conserved, or there's an external force, so linear momentum is not conserved, something like that. So that last sort of throwaway part of this FRQ was worth 2 points. So that ends our Unit 1 short answer FRQs.